Hello, friends, and welcome back to the Snoozy Scientist, where we gently explore the mysteries of our world, one sleepy yawn at a time. Whether you're lying in bed, tucked warmly beneath the covers, or simply floating in that in between space where thought begins to blur, you're exactly where you need to be. Far below, in the oceans of the Atlantic, lies a stretch of water that has haunted sailors and pilots for generations. The Bermuda Triangle, a place where ships set sail and never return, where aircraft vanish mid flight, and where entire crews seem to dissolve into the silence of the sea. But what if I told you the ocean is not the only place with such a reputation? High above our planet, in the silence of orbit, there exists another triangle, invisible to the eye, yet feared by astronauts and scientists alike. A place where satellites falter, where computers suddenly fail, losing their memory without warning, and where astronauts report strange and unexplainable sensations. They have reported seeing phantom flashes of light in this region, lights that still appear in their vision even if their eyes are closed. NASA and the European Space Agency deliberately reroute instruments when crossing this area. Spacecraft passing through here fail without warning. Satellites shut down unexpectedly. Instruments glitch into silence. Entire missions worth millions have been lost in its invisible grasp. This isn't science fiction, it's real and it's expanding. Scientists call this place the South Atlantic Anomaly, but to many it is something else, the Bermuda Triangle of space. But why does this even happen? Is there an explanation for machines dying hundreds of miles above Earth? Why do astronauts see sparks in the darkness? And could the space hold more hidden traps waiting for us to discover? Tonight, we'll drift slowly, patiently, through this anomaly in the sky, exploring what scientists know, what they fear, and what they have yet to uncover. If you enjoy videos like this, soft, soothing, and filled with the quiet wonder of science, I'd love it if you gave this one a like and maybe tap subscribe if you haven't. It helps more curious minds find their way to this peaceful little corner of the internet. And if you're still awake enough to type, let me know in the comments where you're listening from and what time is it where you are. It's always amazing to see curious minds in different time zones falling asleep to the same gentle science stories. Now take a deep breath, close your eyes if you like, and let's begin. Since the first sailors traced lines across their maps, the sea has been a place of both wonder and unease. Vast, indifferent, and untamed, it has swallowed its share of vessels without explanation. Among the countless waves and currents, one region in particular became a symbol for all the ocean's hidden dangers, the Bermuda Triangle. This patch of the Atlantic, roughly bounded by Miami, Bermuda, and Puerto Rico, rose to fame not because of how many ships or planes were lost, but because of how they seemed to vanish. Calm skies, clear waters, no distress calls, compasses that pointed nowhere useful, stories retold so often that the name itself became shorthand for mystery. The Bermuda Triangle lingered in culture because it captured something universal, our fear of losing direction, of watching human certainty dissolve into silence. It was never just about storms or wreckage. It was about the unsettling idea that the world still holds places where the rules we depend on no longer apply. Yet the oceans are not the only stage where this story plays out. High above Earth, circling far beyond the reach of tides, there is another triangle, one not born of rumor, but revealed through data, invisible to the eye, yet undeniable to the machines and people who pass through it. Scientists call it the South Atlantic Anomaly. It has no waves, no storms, no landmarks at all, but it carries the same sense of unease once whispered about the seas, and in many ways it is stranger. Instruments falter here, Space agencies take note of its boundaries. Astronauts know when they are inside it, even without looking through their windows. The legend of the Bermuda Triangle gave us the language of mystery. The anomaly above South America gives us its reality, a place not of folklore but of physics, not imagined by storytellers but traced in the precise maps of science. And unlike the myths of the Atlantic, this triangle is not fixed. It drifts, it grows. Its presence shifts across decades, leaving scientists to wonder what hidden forces inside the Earth give rise to this scar in our planet's shield. If the seas have their Bermuda Triangle, the skies above South America hide their own. This region is not marked by buoys or lighthouses, and no map of the ocean can show its borders. Instead, it drifts quietly in the invisible layers of space just above the Earth, shaping and reshaping itself across the decades. Scientists call it the South Atlantic Anomaly, a patch in our planet's magnetic shield that behaves like no other. Imagine looking down from orbit onto the globe. To the east lies the vast Atlantic Ocean, to the west the curve of South America. Somewhere over Brazil, and stretching far out over the waves, the planet's invisible armor bends and dips. The protective magnetic field that usually keeps cosmic radiation at bay grows weaker here, allowing high-energy particles to sink closer to the Earth than they should. If you could see this region with your eyes, it might appear like a bruise spreading across the surface of a sphere, soft at the edges, darker in the middle, shifting slowly as the years pass. The footprint of this anomaly has never stayed still. In the middle of the 20th century, it was smaller, centered more tightly over the southern Atlantic. With time, it began to drift westward, stretching farther across Brazil, then creeping toward Africa. Decade by decade, its reach widened until satellites charted, extending like a shadow, hundreds of miles across. It is not a perfect circle or triangle, but more like a shifting cloud of danger that satellites and spacecraft must carefully track. What unsettles engineers and astronauts is that the anomaly does not only move, it changes shape. Some years it thins out, becoming less concentrated, but spreading wider. Other years it contracts, gathering its intensity into a denser, more dangerous zone. In recent measurements, scientists have noticed the strange development of not one, but two distinct centers within it, like a cloud splitting apart while still remaining part of the same storm. This split has deepened the mystery, as it suggests that the forces shaping the anomaly are more complex than a single weak spot in Earth's field. The first hints of the anomaly came with the dawn of the space age. Early satellites launched into orbit began to behave strangely as they passed over the South Atlantic. Instruments that had worked flawlessly elsewhere suddenly glitched, memory chips were corrupted, and sensitive detectors fell silent. At first, it was thought these failures might be due to mechanical faults, poor design, or even coincidence, but as more satellites fell victim to the same invisible problem in the same region of sky, a pattern became undeniable. One by one, the data revealed a scar in Earth's magnetic shield. By the 1960s, researchers were already mapping the boundaries of the South Atlantic Anomaly, tracing where instruments began to fail and where they returned to normal. The reputation of this place grew quickly among space agencies. Astronauts were warned about it, satellite operators logged it as a danger zone, and mission planners began to adjust their systems to endure the passage. It became, in quiet technical language, a no-go zone, not because spacecraft could avoid it entirely, but because they had to treat it with respect, the way sailors treat reefs or pilots treat mountains. The story of the anomaly is also the story of careful watching. Decade after decade, satellites have recorded its drift and its changing boundaries. Data show it expanding westward, pulling slowly across the Atlantic toward Africa, as though the magnetic shield itself were tilting under forces we do not fully understand. The recognition of its slow growth has added urgency to its study. A small weakness can be tolerated, but a weakness that grows suggests something deeper at work within the heart of the planet. When astronauts aboard the International Space Station look down at Earth, they do not see this region with their eyes. The oceans below appear calm, the clouds drift in their endless cycles, yet their instruments tell a different story as they pass over the anomaly. Sensors register higher levels of radiation, computers become more vulnerable to glitches, and the crew themselves know they are crossing through a place where space feels less friendly. From the first confused engineers in the early days of orbit to the detailed maps created by modern space agencies, the South Atlantic Anomaly has grown from an unexplained nuisance into one of the most closely monitored regions above our planet. Its footprint over South America and the Atlantic is a reminder that even the invisible protections we rely on can weaken, shift, and change, sometimes in ways that leave us struggling to keep up. The South Atlantic Anomaly does not strike with waves or storms. Its victims are not sailors or pilots, but machines, delicate instruments, computers, and satellites, each one carrying years of human ambition, fall silent in its presence. What the Bermuda Triangle is to ships, this anomaly has become to spacecraft, a place where technology falters, memory slips, and missions sometimes end before their time. The first hints came in the middle of the 20th century, during the early age of satellites. Operators on the ground began to notice strange behavior whenever their machines crossed the skies over South America and the South Atlantic. Instruments that worked perfectly in other parts of orbit suddenly misbehaved. Radiation counters spiked with no clear cause. Data transmissions arrived scrambled, as if the spacecraft had forgotten its own language. Commands that should have been simple produced garbled responses, and in some cases, systems reset without warning. At first, these incidents could be dismissed as the normal growing pains of a young space program. Electronics in orbit were still new, and failures were expected, yet patterns soon became undeniable. The malfunctions always seemed to occur in the same stretch of sky. No matter which nation launched the satellite, no matter its design or purpose, problems gathered like storm clouds when it passed through that invisible zone. The anomaly was gaining a reputation. One of the most famous spacecraft to feel its grip has been the Hubble Space Telescope, designed to open humanity's eyes to the farthest galaxies. Hubble's detectors are so sensitive that they can record the faintest trace of starlight, but when it drifts through the anomaly, those detectors must be turned off. The telescope's vision is closed deliberately, not because of mechanical weakness, but because the radiation in that zone is strong enough to blind its instruments or corrupt its memory. For those brief stretches of orbit, Hubble is forced into silence, drifting like a ship with its sails lowered, waiting until it is safe to see again. Other satellites have not been so fortunate. Weather monitors meant to track storms have suffered unexplained resets. Communication satellites carrying signals across continents have had their data storage corrupted, reducing information to static. Scientific instruments designed for precision measurements have failed entirely, leaving missions crippled after only a fraction of their expected lifetimes. Each failure represents more than just machinery lost. It is years of planning, billions of dollars in combined investments, and countless hours of human effort undone by an invisible hazard. The costs ripple outward. A failed communication satellite can disrupt broadcasts, navigation signals, and emergency transmissions. A broken scientific probe can mean the permanent loss of a once-in-a-lifetime observation. Some missions are designed to capture data during a fleeting planetary alignment or a rare astronomical event. If systems fail during that window, the opportunity may never come again. Entire scientific questions remain unanswered, simply because a spacecraft passed through the wrong patch of sky. These failures have forced engineers to adapt. Modern satellites are built with shielding around their most vulnerable electronics. Redundant circuits provide backup if one system is struck down. Mission planners deliberately schedule instrument shutdowns when crossing the anomaly, treating it as a dangerous but predictable storm. Operators on the ground learn to wait, holding their breath as the spacecraft drifts through the region before reawakening its systems. Even with all these precautions, the hazard never disappears. Each passage carries the chance of a glitch, a failure, or a loss too great to repair. The South Atlantic Anomaly has shaped not only how satellites are built, but how they are operated. It is a reminder that space is not a perfect vacuum of silence and safety. Invisible forces press against the walls of every orbiting machine, probing for weaknesses, testing the limits of engineering. In this way, the anomaly is less a mystery of disappearance and more a quiet predator, capable of erasing memory, corrupting data, or silencing a spacecraft without leaving a trace of violence behind. For those who study it, the phrase Bermuda Triangle of space is not just metaphor. It reflects the reality that this region has claimed victims again and again, not by sinking ships beneath the sea, but by reaching into circuitry and unraveling the fragile order of machines. The silence it leaves in place of once clear transmissions is no less haunting. And though machines have suffered most visibly, the anomaly does not confine its reach to electronics alone. It also surrounds those who travel within it, pressing against their bodies in ways that data alone cannot describe. Machines may have been the first casualties of the South Atlantic Anomaly, but they were not the only ones to reveal its reach. When human beings began to spend long stretches of time in orbit, the story of this strange region gained a new dimension. It was no longer only about circuits scrambled or satellites falling silent. It became about what it feels like to pass through the anomaly in the flesh, to have one's own body respond to invisible forces with sensations that defy explanation. Astronauts aboard the International Space Station cross the anomaly multiple times each day. The station circles Earth every 90 minutes, and its path takes it directly over South America and the South Atlantic, the heart of the anomaly's influence. To the eye, the view is unchanged. The ocean glitters below, clouds swirl in their endless patterns, and the thin atmosphere glows faintly against the curve of the planet. Yet inside the station, the astronauts know when they are crossing the invisible boundary. Their bodies tell them. One of the most vivid and unsettling experiences is the sudden appearance of phantom lights. Astronauts describe them as flashes or streaks across their vision, even when their eyes are closed. They appear in many forms: sharp pinpoints that resemble stars, glowing trails that arc like meteors, or sudden bursts of brilliance like a camera flash going off in the dark. These lights come uninvited. They arrive in the stillness of rest, as astronauts drift in their sleeping bags, or in quiet moments when they float through the station's modules. The lights are not outside the windows, they are inside, carved directly into the retina and the optic nerve by particles that have traveled across the cosmos. Scientists explain that high-energy protons and cosmic rays, slipping through Earth's weakened magnetic shield in this region, strike the sensitive tissues of the eye and nervous system. The flashes are, in effect, the universe writing directly onto the human body. Yet for the astronauts who see them, the explanation does little to erase the strangeness. They are reminded that their flesh and senses are not sealed off from space. They are part of the experiment, their very cells a canvas for invisible radiation. The anomaly does not stop at visions of light. Radiation levels rise measurably as the station drifts through, and even the best shielding cannot fully block the particles. Astronauts have reported feeling slightly unwell, with headaches, fatigue, or waves of nausea that seem to pass once they leave the region. These symptoms are rarely severe, but they are enough to mark the anomaly as different from any other stretch of orbit. A body that is otherwise adapting smoothly to the microgravity environment suddenly feels off balance, a little less stable, as though the invisible forces pressing against it have found a way inside. Testimonies reveal something more difficult to measure as well, a shared unease that settles over crews whenever the anomaly appears on their tracking screens. They know when they are crossing it, not only because of the flashes of light in their eyes or the rise in radiation levels, but because of the atmosphere that creeps into the cabin. Astronauts have compared it to passing through a haunted zone, where the walls of the station seem thinner and the silence of space seems heavier. These are men and women trained to remain calm in the face of fire, vacuum, and mechanical failure. For them to describe a stretch of orbit in such terms says much about the power the anomaly exerts on the human imagination as well as the body. There is a rhythm to these encounters. Orbit after orbit, the International Space Station glides into the anomaly, drifts within its reach for several minutes, then emerges again into safer skies. Each crossing is temporary, yet none go unnoticed. Over time, astronauts learn to expect the flashes, the subtle discomfort, and the tension that lingers until they have passed through. In their logs, the anomaly is not only a radiation spike to be measured, it becomes a recurring character in the story of their mission, a shadow that waits in the same place, always present, always felt. These accounts blur the line between objective science and lived experience. Instruments can chart the rise of radiation and record the energy of incoming particles, but they cannot capture what it feels like to have the universe touch your eyes directly, or to drift through an invisible scar in Earth's protective field with only thin metal walls as a shield. Those details live in memory, in words passed down from one crew to the next, reminders that the anomaly is not just a technical hazard, but a human one. For scientists on the ground, astronaut testimonies provide something irreplaceable. They are not only anecdotes, but evidence of how deeply the South Atlantic Anomaly reaches into machines, into missions, and into the very people who carry them out. Far above the landscapes we know, past the highest clouds and the thin blue edge of the sky, Earth wears an invisible cloak. It cannot be seen or touched, yet it is as real and vital as the air we breathe. Without it, our world would be a place scoured by radiation and stripped bare of atmosphere. This unseen guardian is Earth's magnetic field, a vast shield that stretches tens of thousands of miles into space, enfolding the planet in a protective bubble. The story of this shield begins not in the heavens, but in the depths of the Earth itself. At the very center lies a solid inner core surrounded by a swirling ocean of molten iron and nickel. This restless movement of metals generates powerful electrical currents, and those currents weave together to form a magnetic field. Rising from the depths, it pushes outward through the mantle, through the crust, through the air and beyond, extending into space like the glow of an unseen lantern. This field is not a simple circle. The constant breath of the sun, called the solar wind, presses against it day and night. On the side facing the sun, the shield is squeezed inward, compressed by streams of particles racing from our star at hundreds of miles per second. On the opposite side, the field stretches outward like a tail in the wind, forming a long wake that trails into the darkness of space. Scientists call this protective envelope the magnetosphere, and within its embrace, Earth is spared the full violence of the solar storm. But the magnetosphere is not empty. Within it, radiation becomes trapped in great belts that circle the planet. In the late 1950s, the physicist James Van Allen and his team discovered these zones using early satellites, and they remain one of the most important features of Earth's space environment. Imagine two vast rings, one closer to Earth and another farther away, each filled with energetic particles caught in the loops of the magnetic field. These Van Allen belts are like invisible rivers of radiation, their currents guided along arcs that link the North and South poles. On the surface of Earth, we live beneath this hidden system without feeling it. The thick blanket of atmosphere, coupled with the strength of the field above, shields us from its effects. Yet for spacecraft, the belts are impossible to ignore. Engineers carefully calculate orbits to avoid lingering too long within them. Satellites that operate between the belts must carry heavy shielding, while missions to the moon or other planets are timed to pass through the regions as quickly as possible. The Van Allen belts set the rules for where and how we travel beyond our atmosphere. The magnetosphere is often described as Earth's first line of defense. Its power is not absolute, but it is constant, working silently every second to divert most of the dangerous particles that stream from the sun and drift in from deep space. Without it, the planet would be exposed in ways difficult to imagine. Mars provides a stark lesson. With only a weak and patchy magnetic field, Mars has lost most of its atmosphere to the solar wind over billions of years, leaving behind a dry, barren surface. Earth has been spared that fate by the persistence of its magnetic cocoon, yet, like all shields, it has weak points. Over South America and the Atlantic Ocean, the magnetic field dips closer to Earth, allowing the inner Van Allen belt to brush unusually near the surface. This is the region known as the South Atlantic Anomaly, where satellites encounter harsher conditions than anywhere else in low orbit. Though invisible to the eye, this thinning of the magnetic armor is carefully tracked on charts and woven into mission plans. To astronauts and engineers, it is a reminder that even our planet's great shield is not flawless. The magnetosphere remains one of the most extraordinary features of Earth, a structure both fragile and immense, born from molten motion deep inside the planet, shaped by the breath of the sun, and laced with belts of radiation. It is an unseen architecture that makes life possible. Its presence is constant, yet its imperfections, like those revealed in the South Atlantic Anomaly, remind us that the shield is not uniform. In the invisible ocean of space, Earth carries both strength and vulnerability, wrapped in a cocoon of force that both protects and reveals. Beyond the reach of storms, beyond the familiar tug of gravity, the universe carries dangers that move without sound or color. Among the most insidious of these are cosmic rays, high-energy particles hurled across space from violent events. The death throes of exploding stars, the maelstroms around black holes, and the restless activity of distant galaxies. These particles travel immense distances, silent and unstoppable, until they strike whatever lies in their path. Here on Earth, we rarely sense them. The layers of atmosphere above our heads scatter and weaken the incoming storm, breaking the force of the rays before they can reach us in full. The magnetic field too bends many of them aside, guiding their paths into long arcs around the planet. What reaches the ground is diluted, softened, a drizzle that passes unnoticed into our daily lives. But in orbit, the story is harsher. Stripped of the atmosphere's thick cushion, astronauts and spacecraft are far more exposed to these invisible storms. And in certain regions, such as the South Atlantic Anomaly, the shielding that normally deflects them thins, allowing more particles to slip through. It is there, in the dim quiet of a spacecraft, that astronauts begin to feel the subtle fingerprints of radiation upon their bodies. One of the most curious effects shows itself in the eyes. Astronauts have described phantom flashes of light that appear without warning, streaking across their vision even when their eyes are tightly shut. They resemble shooting stars or sudden bursts like the flare of a camera. These are not tricks of imagination. They are the direct result of energetic particles striking the retina, jolting the cells into firing as if they had seen light. In reality, what they are sensing is the universe touching the nerves of the eye directly. Yet the impact does not stop there. Cosmic rays penetrate deeply, passing through tissues, colliding with molecules, and leaving behind tiny scars at the cellular level. They can slice through strands of DNA, the genetic instructions that every cell depends on to function and repair itself. In many cases, the body's repair systems manage to fix the damage, patching the broken code with remarkable precision. But the damage is not always clean. A mistake in repair can leave behind a mutation, a change that lingers in the quiet machinery of life. With each pass through a high radiation region, astronauts accumulate more of these invisible marks. Most of them will never matter, but over time, the risks mount. The body is not built to endure such constant bombardment. Eyes may grow cloudy with cataracts sooner than they would on Earth. The immune system may falter, responding more slowly to threats. The chances of cancer rise, not immediately, but as a shadow cast years into the future. Even the brain, shielded within the skull, may be touched in subtle ways. Studies suggest that memory and mood could be altered by repeated exposure to cosmic radiation, though these effects are still being unraveled. Unlike a broken circuit in a machine, damage to living tissue cannot always be undone. The repair may fail, the mutation may persist, and because radiation is invisible and silent, there is no warning when the strike arrives. It simply passes through, leaving its trace behind. For astronauts aboard the International Space Station, circling the Earth 16 times a day, each orbit is a reminder of this reality. The South Atlantic Anomaly is marked clearly on their charts. They know when they are passing through, not by looking out a window, but by the sudden flashes in their vision or the spike on a radiation monitor. The station itself is shielded, yet shielding has limits. No matter how carefully designed, some particles always slip through. The danger is cumulative. A single crossing of the anomaly is not deadly, but hundreds of passes add weight to the risks. Time spent in orbit becomes a calculation of dosage, measured not only in days and weeks, but in how many times the body has endured the silent storm. Engineers plan missions carefully to limit exposure, but no amount of planning can remove it completely. It is here that the difference between human and machine becomes stark. A satellite struck by a cosmic ray may glitch, reset, or even fail entirely, but it does not carry scars into the future. Humans do. Each particle that alters DNA, each fragment of radiation that lingers in a cell, is carried forward in time. It is why radiation has been called the silent assassin of space exploration, not because it strikes with sudden violence, but because it leaves marks that are felt long after the moment has passed. For those who dream of traveling beyond Earth, to the Moon, to Mars, and farther still, this assassin is always part of the calculation. Machines can be replaced, data can sometimes be reacquired, but the body remembers every particle, every invisible wound, and carries them home. Beneath our feet, far below the crust and mantle, lies a restless heart of molten metal. Earth's core is a place we will never visit, a furnace of liquid iron swirling under pressures so intense that solid rock behaves like flowing water. Though hidden, this secret heart leaves fingerprints on the surface, marks that scientists can read if they know where to look. The South Atlantic Anomaly is one such mark, a clue that tells us something unusual is stirring deep inside the planet. When researchers traced the weakness of the magnetic field over South America, they followed the invisible lines of force downward. What they found was striking. Beneath the continent, In the liquid layers of the outer core, there is a patch of reversed magnetism. Instead of adding strength to Earth's field, this pocket fights against it. It is known as reverse flux, a patch where the normal order of magnetic flow is turned on its head. This strange reversal weakens the shield above. Just as two opposing waves can cancel each other out, the reversed field beneath South America works against the larger magnetic system. The result is a thinning, a vulnerable region where the protection that normally guides radiation away from Earth grows faint. The anomaly we see above the Atlantic is the surface reflection of something far deeper, a sign of the turbulent dance of molten iron below. The movement of Earth's core is never still. Rivers of liquid metal churn and swirl, driven by heat escaping from the solid inner core and the rotation of the planet itself. These flows generate electricity on a colossal scale, and that electricity sustains the magnetic field. But the motions are not uniform. They surge, twist, and bend, creating zones where the field becomes stronger or weaker. From time to time, the patterns shift dramatically and patches of reverse flux emerge. Over South America, one of these reversed patches has grown persistent. It may have first appeared thousands of years ago, but only now, with the aid of satellites, can we see its true outline. The South Atlantic Anomaly is not simply a flaw in the shield, it is a direct map of what the liquid iron is doing below our feet. By watching its changes, scientists can glimpse the secret currents of Earth's core without ever drilling into the planet. Data from the European Space Agency's swarm satellites has shown that the anomaly is not a single, static blemish. It is more like a shifting pool, stretching and dividing as the core flows beneath it. In recent decades, the anomaly has even shown signs of splitting into two distinct lobes, each with its own center of weakness. This suggests that the motions within the outer core are complex, perhaps weaving streams of liquid metal in different directions, each tugging at the field in its own way. The link between core motion and magnetic weakness is powerful, but still not fully understood. Some researchers believe the reverse flux beneath South America could be part of a larger process, one that hints at how magnetic fields collapse and reform. Earth's field has flipped many times in the past, with the North and South poles trading places. Each reversal leaves behind traces in rocks and sediments, frozen records of the magnetic confusion that lasted for thousands of years. The South Atlantic Anomaly, and the strange reversed patch that fuels it, may be an early whisper of such a shift. Even if a full pole reversal is still far in the future, the anomaly proves that the core is restless. The solid inner heart of the planet is slowly growing as molten iron crystallizes, releasing heat and stirring the liquid layers around it. Those restless streams carve patterns into the field above, just as winds on the ocean's surface sculpt waves. The anomaly is one wave in that endless sea of motion, an echo of the hidden engine below us. By studying it, scientists gain more than a warning for satellites and astronauts. They also gain a rare window into Earth's deep interior. No probe will ever reach the core. No camera will ever see the swirling rivers of metal firsthand, but the faint crack in the magnetic shield tells us they are there, flowing, reversing, shaping the invisible cocoon that keeps life safe on this planet. Every compass needle on Earth quietly leans on the planet's magnetic field for guidance. It is a trust so steady that sailors, explorers, and aviators have built entire journeys around it. North is north, south is south, and the invisible arcs of force rise gracefully from one pole and fall to the other. Yet beneath this appearance of permanence lies a truth written in stone. The poles have not always held their places. They have wandered, they have weakened, and many times before, they have even reversed. Evidence of these shifts lies frozen in the rocks themselves. When molten lava pours from a volcano and cools into solid basalt, tiny grains of iron within it align with the magnetic field of that moment. Like a compass needle locked in place, these grains preserve the direction of north as it was when the rock hardened, layer upon layer of ancient flows, scattered across the continents, reveal a startling pattern. Some point toward the north we know today, others point the opposite way, their grains captured during times when north and south had switched places entirely. From these geological archives, scientists have reconstructed a record of Earth's magnetic past. The last full reversal took place roughly 780,000 years ago, long before modern humans left their first footprints. But between the full reversals, the record also shows briefer disturbances called excursions. During these events, the poles wander far from their usual positions, sometimes moving closer to the equator before returning again. Each episode unfolds over thousands of years, far too slowly to be noticed in a single lifetime, but unmistakable when traced across deep time. What makes these reversals and excursions so striking is not only their inevitability, but also their consequences. As the poles weaken and drift, Earth's magnetic shield falters. The normally smooth pattern of field lines becomes tangled, with patches of reversed flux rising from the restless outer core. In those times, the protective cocoon around our planet grows thin. It does not disappear entirely, but it becomes less efficient at steering away the charged particles that stream in from the sunlight. The atmosphere absorbs much of the storm, but satellites in orbit and electrical systems on the ground become more vulnerable to interference. Imagine a great umbrella, suddenly patchy, letting in bursts of rain. Navigation would grow confusing. Compasses that once pointed reliably north might swing uncertainly, their needles pulled by strange, shifting lines of force. Auroras, usually confined to the high latitudes of the Arctic and Antarctic, might spill farther toward the equator, painting the skies of regions unaccustomed to such light shows. These shimmering curtains would be a visible sign of particles entering the atmosphere where they usually do not. In our present age, with satellites girdling the planet and spacecraft circling overhead, the implications would be profound. Systems that rely on precise orientation, communication networks, weather monitoring, and navigation satellites could face higher rates of disruption. Engineers already designed spacecraft to endure the quirks of the South Atlantic Anomaly, a localized weak spot in the magnetic field. But during a global weakening, those vulnerabilities would multiply, spreading across orbits once considered safe. This is why scientists pay close attention to the growing footprint of the South Atlantic Anomaly. To some, it is simply a regional irregularity, born of the complex flows in Earth's liquid iron core. To others, it may be a symptom of a larger trend, a whisper of a shift already beginning deep below. Models show that reversals often begin with patches of reverse flux bubbling up inside the core, gradually weakening the overall field before flipping it entirely. The anomaly's presence and its slow expansion raises the question of whether we are witnessing such a step in progress. Supercomputer simulations attempt to capture this hidden process. Fed with data from satellites that track the field daily, they show how the invisible lines of magnetism twist, knot, and eventually reorganize. In these models, the field does not vanish suddenly. It flickers, weakens, and then re-emerges in a new alignment, with north and south trading places. Watching the models unfold is like watching a dance of chaos, elegant and unsettling, the planet's magnetic skin rearranging itself before our eyes. What such a change would mean for life on Earth is still debated. The geological record shows that past reversals left no obvious scars of global extinction. Life adapted, as it always does. Yet, for a civilization dependent on satellites, power grids, and constant communication, the stakes are different. The transition would not stop life itself, but it would test the systems we rely on every day, from the accuracy of a compass to the stability of a global network. And so, the South Atlantic Anomaly is studied not only as a hazard in its own right, but as a possible clue to the future. Whether it fades like countless features before it or deepens into the first step of a reversal, it reminds us that even the most trusted compass direction is written in a language the Earth itself may choose to rewrite. The South Atlantic Anomaly is not fixed in place like a scar carved into stone. It is alive, restless, and slowly expanding across the skies. From the first measurements taken by satellites in the middle of the 20th century, scientists have noticed that this patch of weakness has not remained constant. It stretches, drifts, and thickens like a bruise spreading across the invisible skin of Earth's magnetic shield. Data from decades of observations show a steady trend. The anomaly, once relatively small, now spans a vast region over South America and the South Atlantic Ocean. It covers millions of square kilometers, an area large enough to swallow whole countries beneath its reach. What makes it even more unsettling is that it is not just expanding, but also splitting into multiple lobes, each with its own center of weakness. These lobes shift like clouds of radiation exposure, reshaping themselves as the liquid core below churns. Scientists studying the anomaly with the European Space Agency's swarm satellites have traced its growth with remarkable precision. Since the 1950s, the field strength in the region has weakened significantly, and the anomaly has grown broader. The data suggests that it is not finished. Its slow crawl westward, combined with its spreading footprint, hints that the anomaly may one day reach farther across the globe, altering the safety of orbits that satellites currently rely on. For satellites, this steady expansion is a quiet menace. Each time a satellite passes through the anomaly, its delicate circuits are exposed to higher doses of energetic particles than they would experience elsewhere in orbit. Instruments can freeze, computers can lose data, and sensors can be overwhelmed. In some cases, the damage is recoverable, with systems rebooting once they leave the zone. In others, entire missions have ended prematurely, cut short by exposure in this silent trap. As the anomaly grows, the frequency of these crossings increases. Orbits that were once safe begin to pass through danger, and the list of spacecraft vulnerable to its reach grows longer. For the International Space Station, the expansion is more personal. Astronauts living and working on the station cannot avoid the anomaly entirely. When the station drifts through it, the crew sometimes powers down sensitive instruments, shielding them from damage. The astronauts themselves are exposed to higher levels of radiation during these passages, though shielding and limited exposure keep them safe in the short term. The knowledge that the anomaly is widening adds weight to long-term concerns about human health in space. The implications extend beyond Earth orbit. Future missions to Mars will need to travel through regions influenced by Earth's magnetic environment before setting sail into interplanetary space. An expanding anomaly means new calculations for trajectories, shielding, and timing. Engineers will need to design spacecraft that can withstand not only the storms of sunlight, but also the subtle scars of Earth's own shifting field. The idea that our planet, which has always sheltered us, could complicate our path to the stars is both ironic and sobering. The image of the anomaly as a hole in Earth's shield is a powerful one. Imagine a knight's armor, once gleaming and strong, developing a thinning patch where blows can slip through. The rest of the armor still holds, but the weakness spreads, and every strike aimed there grows more dangerous. The South Atlantic Anomaly is that thinning patch, a region where the invisible armor of the magnetosphere has grown frail. It does not threaten life on the surface directly, because our atmosphere still absorbs much of the radiation, but for the fragile machines and brave humans orbiting above, it is a place of vulnerability that cannot be ignored. As scientists continue to map its contours, they face the uneasy truth that the anomaly is not shrinking. It is alive, dynamic, and persistent. Its steady growth whispers of the turbulent currents in the core, of the restless heart of molten iron that drives our magnetic shield. Each year of data adds another line to a story still being written, one in which the anomaly's future remains uncertain and its reach perhaps still unfinished. If Earth can host such a strange flaw in its shield, it is tempting to wonder what else might be out there. The South Atlantic Anomaly reminds us that invisible dangers can hide close to home, yet Earth is only one world in a vast universe. The thought lingers like an open question. If space above our own planet holds such a trap, might the cosmos itself be scattered with similar anomalies, quiet regions where forces gather and bend in ways we do not yet fully understand? Astronomers, peering through the lenses of their telescopes and the algorithms of their mathematics, have long known that space is not as empty as it appears. The stars may look scattered randomly across the sky, but deeper study reveals patterns, shapes, and structures woven into the fabric of the universe. Some of these patterns are visible, painted in starlight or glowing gas. Others can only be uncovered by following subtle clues, like detectives tracing a hidden path. Sometimes the clues arrive as faint distortions in light. When light from a distant galaxy passes through an invisible mass, it bends and warps, a phenomenon known as gravitational lensing. By measuring these distortions, astronomers can map places where matter is present but unseen. What they find are regions dense with invisible weight, made not of stars or planets but of dark matter, a substance that does not glow or reflect, yet shapes the universe on its grandest scales. These zones behave like cosmic reefs, altering the flow of energy and matter, much like the South Atlantic Anomaly alters the smoothness of Earth's shield. Other times, the clues appear in silence rather than distortion. Telescopes scanning wide swaths of the sky sometimes stumble upon voids, immense bubbles where almost nothing exists. These regions are not completely empty, but they contain far fewer galaxies than expected. Their vastness makes them haunting, stretching across hundreds of millions of light years. In the middle of such emptiness, space itself feels like a desert, a place where the normal rhythm of cosmic structure seems to falter. For astronomers, these voids raise questions that echo the mystery of Earth's own anomaly. Why should matter be absent in such immense volumes, and what forces carved out these hollows? The discovery of these invisible traps often comes not from dramatic pictures, but from careful mathematics. Astronomers measure the positions of galaxies, the brightness of stars, and the speed of cosmic flows. They chart maps of the universe that look like vast spider webs, with clusters connected by filaments and separated by yawning gaps. The patterns emerge slowly, almost like a photograph developing in a dark room, until the hidden shapes reveal themselves. Much as sailors once relied on charts of reefs and shoals to navigate dangerous seas, scientists now build cosmic charts that mark zones of mystery. Some are regions of overwhelming gravity, where black holes sit quietly until they consume. Others are stretches of emptiness, where galaxies should be but are not. Still others are hidden layers of invisible matter, bending and shaping the light of distant worlds. Each one is a reminder that the universe is not uniform, but scattered with both abundance and absence, each carrying its own risks and wonders. If Earth's magnetic anomaly can grow and change over decades, then cosmic anomalies remind us that even the universe itself shifts on scales both large and small. The cosmos is alive with hidden structures, and each discovery only sharpens the sense that there may be countless more waiting just beyond the reach of our instruments. Astronomers can only follow the faint trails of evidence, like footprints fading in sand, and trust that mathematics and persistence will slowly uncover what the eye alone cannot see. Far beyond the reach of our own Milky Way, past the spiral arms and the faint halo of stars that surround us, there is a force that tugs quietly on our entire galaxy. It does not shine. It does not announce itself with light or color, yet astronomers have discovered that it is pulling us and thousands of neighboring galaxies toward a mysterious point in space. They call this hidden destination the Great Attractor. The first hints came in the middle of the 20th century when astronomers began to chart the motions of galaxies on a grand scale. Using redshift measurements, they could see which galaxies were moving away due to the expansion of the universe and at what speed. But when the data was gathered across wide regions of the sky, something strange appeared. The Milky Way and many of the galaxies near us were not simply drifting outward with cosmic expansion, they were all moving in the same direction, as though caught in a giant current. It was as if an invisible gravity well were pulling entire clusters toward a place we could not see. The scale of this pull is staggering. The Great Attractor lies hundreds of millions of light years away, in the direction of the Centaurus and Hydra constellations. Despite that distance, it influences the motion of galaxies across a vast region of space. Imagine a whirlpool so immense that even boats far from its center begin to feel its pull. That is what the Great Attractor is to galaxies, a gravitational force unlike anything else we have measured nearby. And yet, it remains elusive. The trouble is that this strange region sits directly behind the plane of our own galaxy. When we look in that direction, the view is blocked by billions of stars, thick clouds of gas, and lanes of interstellar dust. Astronomers call this obstruction the zone of avoidance, because for decades it was nearly impossible to see through. The Great Attractor hides behind this curtain, revealed not by its light, but by its influence on everything around it. To study it, astronomers have had to rely on indirect methods. Radio telescopes can peer through dust that blocks visible light. Infrared instruments can detect the faint glow of galaxies obscured by the Milky Way's disk. By combining these tools, researchers have slowly mapped some of the hidden structures in this part of the sky. They found galaxy clusters and superclusters stretching across enormous distances, stitched together in a gravitational web. The Great Attractor appears to sit within a larger structure known as the Laniakea supercluster, of which our own Milky Way is a tiny part. Even so, the true nature of the Great Attractor is uncertain. Some scientists believe it is simply the center of mass of a very large cluster of galaxies, combined with the gravitational pull of dark matter we cannot see. Others suggest that its strength may be amplified by even larger structures, such as the Shapley supercluster, lying beyond it. In this view, the Great Attractor might not be a single object at all, but rather a convergence zone, a place where gravity from multiple sources collects into one irresistible tug. What makes it especially haunting is the comparison to anything else we know. Black holes, for example, are powerful, but their pull is felt on smaller scales, swallowing stars or nearby material. The Great Attractor is different. Its influence stretches across hundreds of millions of light years, binding the movements of entire galaxies. It is gravity at its most majestic, reshaping the flow of the universe on a scale that dwarfs imagination. And yet, we cannot look at it directly. It does not glow like a quasar, nor shine like a supernova. It is a phantom in the cosmic dark, its presence revealed only by the way it bends the paths of galaxies like invisible hands guiding dancers across a floor. To this day, no telescope has pierced the veil enough to show its full form. We see only the evidence of its pull, never the body of the thing itself. For astronomers, the Great Attractor is a reminder that the universe is layered with mysteries. Even as our instruments grow sharper, some truths remain hidden behind veils of dust, distance, and darkness. We know it is there, we can measure its influence, yet its identity slips away, retreating deeper into the unknown. When astronomers map the universe, they often expect to find stars and galaxies scattered like glitter across a black canvas. Yet sometimes, the most startling discovery is not what is there, but what is missing. One of the largest and most haunting examples of absence lies in the constellation of Bootes. It is called the Bootes Void, a bubble of almost nothing stretching across roughly 330 million light-years. To imagine its scale, picture our own Milky Way galaxy, with its spiral arms of hundreds of billions of stars. Now place thousands of galaxies together, each one filled with its own stars, planets, and nebulae. That is what a typical region of the universe contains. But in the Bootes Void, the expected abundance falls away. There are only a few scattered galaxies, like lonely lanterns floating in an endless night. Compared to what should exist in such a space, the void is astonishingly barren. The discovery of the Bootes Void came in the 1980s, when astronomers were surveying galaxies using powerful telescopes. They charted redshifts, a method that shows how far galaxies are by measuring the stretching of their light. As the map of this region took shape, something shocking appeared. Instead of a dense field of galaxies, there was a yawning gap, a great bubble of darkness where hardly anything existed. The Bootes Void looked like a hole carved into the cosmic web. What makes this void especially strange is not only its size, but the contrast it creates. The universe is structured like a vast net, with galaxies clustering in filaments that weave across space. Between those filaments lie empty gaps, but none as large as the Bootes Void. It is as if someone pressed a giant thumb into the web of galaxies, leaving behind a hollow pocket. Even the galaxies that do exist within the void appear unusual, sometimes stretched into chains as if drawn toward the edges, trying to escape the emptiness. For astronomers, the existence of such a massive void was unsettling at first. According to the standard models of cosmology, matter in the early universe should have spread fairly evenly before clustering under the pull of gravity. A hole the size of the Bootes Void seemed far too large to emerge naturally in the amount of time the universe has existed. Its discovery pushed scientists to refine their models of cosmic evolution. They realized that the growth of structure in the universe was shaped not only by visible matter, but also by the vast sea of dark matter and dark energy. These unseen components helped explain how such immense bubbles of emptiness could coexist with regions of extreme abundance. The Bootes Void revealed something profound. Emptiness is not a mistake or an anomaly. It is part of the architecture of the cosmos. Just as sound requires silence to be heard and light needs darkness to shine, the great clusters of galaxies only make sense when set against the backdrop of such immense voids. The Bootes Void became a landmark, proof that the universe is not uniform but patterned, woven from a balance of crowded filaments and quiet hollows. Standing in imagination at the edge of the Buddha's void is like staring across an ocean without end. A few faint galaxies glimmer in the distance, but for hundreds of millions of light years in every direction, there is mostly nothing. The sheer scale of this emptiness challenges our sense of what is normal. We often expect the universe to dazzle us with more stars, more light, more matter. Yet here, the wonder lies in less. This discovery gave astronomers a new lens for understanding the universe. It showed that the cosmic web is not just a structure of galaxies, but also of voids, each as important as the other in shaping the vast design. The Buddha's void, once a puzzle, became a reminder that even emptiness has meaning. Its silence tells part of the story of how matter spread, clumped, and organized itself into the universe we see today. At the far edge of our solar system, beyond the orbit of Neptune, lies a region filled with icy relics from the dawn of planetary history. This expanse is called the Kuiper Belt, a vast ring of frozen bodies circling the sun like a scattered halo. For decades, astronomers imagined it as a bustling frontier, crowded with dwarf planets, comets, and countless fragments of ancient rock and ice. Yet, when they began to measure it carefully, they found something that took them by surprise. The Kuiper Belt does not stretch endlessly outward into the dark. Instead, it comes to an abrupt and puzzling edge, a sudden thinning known as the Kuiper Cliff. The name suits it well. Imagine hiking across rolling hills that extend for miles, only to find that the ground drops sharply into a canyon. That is what the Kuiper Belt does in space. For a long distance beyond Neptune, icy bodies appear in great numbers. Pluto, Eris, Haumea, Makemake, and many smaller worlds circle in the cold twilight of the sun. But past about 50 astronomical units, the population drops steeply. The vast crowd of icy debris almost vanishes, leaving a strange emptiness where astronomers expected the belt to continue. When this sudden cliff was first noticed, it startled researchers. The solar system had seemed predictable, governed by the slow and steady laws of gravity. Why, then, would the distribution of objects end so sharply? One theory suggested that the cliff might be the result of gravitational sculpting by Neptune itself. The giant planet could have cleared away much of the debris as it migrated outward in the early solar system. Yet the steepness of the drop was difficult to explain with Neptune alone. This led to more daring ideas. Some scientists proposed that a hidden planet, far larger than Earth, might lurk beyond the Kuiper Belt. Nicknamed Planet 9, it has never been seen directly, but its existence is inferred from the strange orbits of distant objects. A few icy bodies at the solar system's edge seem to cluster together in a way that gravity alone should not allow. It is as if something massive, far beyond Pluto, is tugging gently on their paths. If such a planet exists, it could also help explain why the Kuiper Belt ends so abruptly, shaping the orbits of countless smaller fragments and sweeping the outer region clean. The possibility of Planet 9 has captured the imagination of astronomers and the public alike. Some describe it as a cold giant, perhaps 10 times the mass of Earth, wandering in a long, stretched orbit that carries it hundreds of astronomical units away from the Sun. If true, then the solar system is larger and stranger than we ever imagined, hiding secrets even after centuries of exploration. The Kuiper Cliff might be the first faint fingerprint of this unseen world, a quiet hint of its gravitational influence. Even without Planet 9, the Kuiper Cliff remains a mystery. The emptiness beyond 50 astronomical units is so striking that it challenges our understanding of how planetary systems form. Why would the early solar system, rich with gas and dust, produce a populated belt that suddenly halts rather than tapering off more gradually. Some suggest that passing stars in the distant past may have nudged away the outer material. Others wonder if the original disk of matter from which the planets grew simply ran out of material at that distance. The shock of this discovery lingers because the Kuiper Belt was once imagined as an endless realm stretching outward until it merged with the distant Oort cloud. Instead, the cliff reveals that even our own backyard hides sharp edges and surprises. Space, which seems so smooth and infinite from a distance, turns out to be full of sudden transitions, like hidden steps in a staircase leading into the dark. The Kuiper Cliff reminds us that exploration often begins with expectation and ends with surprise. Astronomers who looked outward from Neptune expected abundance. What they found was silence, a great thinning of worlds where there should have been many. The solar system ends not with a gradual fade, but with a cliff, a reminder that even in the places closest to home, the universe is still capable of startling us. There is a strange paradox at the heart of modern astronomy. When we gaze into the night sky, we see stars, galaxies, and glowing nebulae painted across the darkness. Yet scientists now believe that most of what exists in the universe cannot be seen at all. This hidden majority is called dark matter. It does not shine, it does not reflect, and it does not interact with light in any familiar way. To our eyes, it is completely invisible. And yet, its presence can be felt everywhere, shaping galaxies, bending starlight, and forming invisible traps across the cosmos. The story of dark matter begins with motion. In the early 20th century, astronomers noticed something unusual when they measured how galaxies rotate. The outer stars, far from the galactic center, were spinning much faster than they should have been. According to Newton's laws, those stars should have flown off into space. The only explanation was that something unseen was providing the extra gravity to hold them in place. This invisible glue became known as dark matter. Dark matter reveals itself not by what it is, but by what it does. One of the clearest demonstrations is through gravitational lensing. When light from a distant galaxy passes near a massive cluster, the path of that light bends, much as glass bends light in a lens. Sometimes, this bending creates arcs or rings in the sky, ghostly distortions that show us there is more mass present than the stars alone can account for. In these warped images, we see the fingerprints of dark matter. It shapes light without ever shining itself. Regions filled with dark matter can warp reality in subtle ways. Galaxies do not drift randomly, but instead follow the invisible scaffolding dark matter provides. Vast halos of it surround galaxies, extending far beyond the reach of their visible stars. Between clusters, filaments of dark matter stretch across millions of light years, connecting structures together like strands in a cosmic web. If we could somehow see dark matter directly, the universe would appear as a lacework of glowing filaments and knots, with galaxies simply hanging like dewdrops along the strands. The presence of dark matter means there may be hidden reefs scattered throughout space. Just as coral reefs in the ocean can redirect currents and snag unwary ships, regions dense with dark matter can bend the flow of stars and galaxies. They are made not of stone or living organisms, but of pure gravity, invisible bulges where mass gathers silently. An unsuspecting spacecraft passing through such a region would not crash into a solid obstacle, but it would feel the tug of a gravitational current stronger than expected. For astronomers, mapping these invisible reefs has become one of the greatest challenges of modern cosmology. What makes dark matter especially haunting is that we do not know what it is made of. Decades of experiments have failed to detect any particle of it directly. It is not ordinary matter hiding in dim stars or cold gas. It is something else entirely, a substance that makes up nearly 5 times more of the universe than everything we can see, and yet it slips through our detectors as though it were a ghost. The only certainty is its gravity, which sculpts galaxies and steadies the universe itself. The thought of invisible reefs stretching across space stirs a quiet unease. If we rely on light to guide us, how many structures are hidden from our sight, bending paths and shaping destinies without our knowledge? For now, astronomers build maps of dark matter using clever mathematics and indirect evidence, charting distortions in starlight and tracing the movements of galaxies. These maps hint at a universe far stranger than the one visible through a telescope. It is a universe where gravity itself forms structures that cannot be touched or seen, yet dominate the shape of all that exists. There are places in the universe where gravity becomes so strong that it bends not only the paths of stars and gas, but the very fabric of space and time. These are black holes, the ultimate traps of the cosmos, regions so extreme that nothing, not even light, can escape once it has crossed a boundary known as the event horizon. To approach this boundary is to approach a line that can never be crossed in reverse, a true point of no return. The event horizon is not a physical surface, but an invisible threshold surrounding the black hole. Imagine sailing across the ocean toward a waterfall so powerful that the current pulls faster than any boat can row. Before reaching the edge, there is a point where escape is no longer possible, no matter how quickly one paddles. That unseen boundary is much like the event horizon, a silent marker where gravity overwhelms every possible path outward. Once crossed, all trajectories bend inward. For stars that wander too close, the consequences are spectacular. The immense tidal forces near a black hole can stretch and tear a star apart in a process known as spaghettification. Its gases spiral inward, forming a luminous disk that whirls around the black hole at incredible speeds. Friction in this disk heats the gas to extraordinary temperatures, causing it to shine brighter than entire galaxies for brief moments. From across the universe, astronomers can sometimes detect these violent meals, sudden bursts of light marking the final moments of stars consumed by invisible giants. Black holes themselves, however, remain unseen unless they feed. Because they trap light completely, they do not glow like stars or reflect like planets. Their presence is betrayed only by the way they affect their surroundings. Gas swirling into an accretion disk, jets of high-energy particles blasting outward at nearly the speed of light, and the orbits of stars, looping around an invisible center, are the signatures astronomers use to trace them. In this way, black holes are like cosmic predators, hidden in darkness until disturbed, their true forms revealed only in the act of devouring. One of the most famous examples lies at the center of our own galaxy. Sagittarius A*, a supermassive black hole with a mass millions of times greater than the Sun, anchors the Milky Way. For years it remained silent, cloaked in dust and faint radiation. But astronomers watched the orbits of nearby stars curve sharply around an unseen mass, their paths moving faster and faster as they approached, as though tethered to a hidden whirlpool. The conclusion was unavoidable. Only a black hole could explain the invisible weight pulling them inward. In some galaxies, the scale is even greater. Supermassive black holes, billions of times heavier than the Sun, sit in their centers, shaping the growth of galaxies themselves. Their immense gravity acts like a conductor, regulating the flow of gas, triggering bursts of star formation, or shutting it down entirely. These black holes are not only silent traps, but also architects, sculpting the galaxies that orbit them. To study black holes is to study the limits of our understanding. Einstein's theory of general relativity predicted their existence, describing how space and time curve under mass. But within a black hole, the equations themselves collapse into infinities, leaving questions science cannot yet answer. What happens beyond the event horizon remains one of the deepest mysteries in physics. Is there a singularity, a point of infinite density, or does nature find another path we have yet to imagine? In this way, black holes echo the eerie allure of the Bermuda Triangle. They are zones of disappearance, places where objects enter and never return, leaving behind only silence and absence. Yet, unlike the myths of ships and planes lost to the ocean, black holes are firmly grounded in observation, their influence mapped across the universe. They are real, they are powerful, and they remain among the most enigmatic phenomena we know. In the vast silence of the universe, where galaxies drift like lanterns on a dark sea, sudden flashes of energy sometimes ripple across the void. They arrive not as beams of light, but as pulses of radio waves, brief bursts so fleeting that they last only a few thousandths of a second. Astronomers call them fast radio bursts, or FRBs, and they remain among the most mysterious signals ever detected in the cosmos. The story of FRBs began in 2007, when researchers analyzing archival data from a radio telescope in Australia stumbled upon something unusual. Buried in the recordings was a sharp spike, a burst of radio waves unlike anything seen before. It had lasted only a few milliseconds, yet it carried more energy than the sunlight emits in days. At first, it was thought to be an error in the equipment, a stray glitch. But as more telescopes turned their attention to the skies, more of these bursts were discovered, each one as sudden and powerful as the first. The strange thing about FRBs is their brevity. In the blink of an eye, they are gone, leaving no trace behind. Yet, by measuring how the radio waves spread across different frequencies, astronomers can tell that these signals come from galaxies far beyond our own. Some lie billions of light years away, meaning that the bursts we detect today were set loose when the universe was younger than it is now. They are whispers from ancient events, carrying secrets across unimaginable distances. Not all FRBs are the same. Some appear only once, single flashes that never repeat, no matter how carefully telescopes return to the same patch of sky. Others return again and again, repeating in irregular patterns, as though whatever engine powers them flickers back to life. In a few cases, repeating FRBs have shown periodic behavior, with signals arriving on a schedule, like the tolling of a distant bell. This diversity has left astronomers puzzled, hinting that there may be more than one source behind these enigmatic bursts. Theories abound, each more intriguing than the last. One leading explanation points to magnetars, a special type of neutron star with a magnetic field trillions of times stronger than Earth's. When the crust of a magnetar cracks under the pressure of its own field, it can unleash a violent flare of energy. Such an outburst could easily power a fast radio burst, producing a pulse that races across the universe. In 2020, a magnetar in our own Milky Way was observed releasing a burst that looked strikingly similar to an FRB, giving weight to this idea. Yet magnetars may not explain them all. Some FRBs seem too energetic, too frequent, or too unusual to fit neatly into that model. Other theories suggest that collisions between compact objects, such as neutron stars spiraling together, could be the cause. Still others imagine more exotic origins, from black hole interactions to as yet unknown astrophysical processes. A handful of voices have even speculated about signals from intelligent civilizations, though most scientists caution that natural explanations, however strange, are far more likely. What keeps the mystery alive is the scale of energy involved. A burst lasting just a few milliseconds can release as much power as hundreds of millions of suns shining together. That such immense forces can be unleashed in such brief moments is almost incomprehensible. It is like hearing a single clap of thunder so loud it could be heard across continents. To catch FRBs, astronomers have built specialized instruments, radio telescopes that can scan wide regions of the sky in real time. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, has become one of the leaders in this field, detecting hundreds of FRBs and revealing patterns that were once hidden. With each detection, the puzzle grows clearer in some places and more tangled in others, as repeating bursts and unusual outliers challenge every theory proposed. Fast radio bursts are a reminder that the universe still holds surprises, even in wavelengths invisible to the human eye. They arrive suddenly, without warning, crossing billions of light years to deliver a brief message we cannot yet decipher. Some come once and vanish forever, others return in strange rhythms, but all of them whisper of forces powerful enough to shake the cosmos in an instant. Across the deep canvas of the universe, there are flashes so powerful that for a few heartbeats, they outshine every star in an entire galaxy. These are gamma ray bursts, sudden eruptions of energy that erupt without warning and vanish almost as quickly. They last anywhere from a fraction of a second to a few minutes, yet in that brief span, they release more energy than our sun's lights will produce in its entire lifetime. Gamma rays are the most energetic form of light, invisible to human eyes, but capable of carrying immense power. When astronomers first detected these bursts in the 1960s, they were not searching the skies for cosmic fireworks. The discovery was accidental. Satellites launched to monitor nuclear tests on Earth picked up mysterious flashes of gamma radiation coming from space instead. At first, the signals were puzzling. Then, as more detections followed, it became clear that the universe itself was the source. What makes gamma ray bursts extraordinary is not only their brightness, but the distance from which we can see them. Many of the bursts recorded come from billions of light years away, yet they still appear dazzlingly intense. To shine so brightly across such vast distances, the events that create them must be among the most violent in existence. There are two main kinds of gamma ray bursts. The short bursts, lasting less than 2 seconds, are thought to come from the collision of neutron stars. These are the dense remnants of massive stars, so compact that a teaspoon of their matter would weigh billions of tons. When two of these stellar corpses spiral together and collide, the impact releases an enormous surge of energy, sending gamma rays racing outward across the universe. The long bursts, which can last from a few seconds to several minutes, are believed to form in the deaths of massive stars. When a giant star runs out of fuel, its core collapses under its own weight, creating a black hole or neutron star at the center. As the star implodes, jets of energy punch through its outer layers and burst into space. If one of those jets happens to be aimed at Earth, our telescopes catch it as a gamma ray burst. The consequences of such an event can be devastating for any planet in the path of the beam. A single burst could strip away the protective atmosphere of a world, bombarding its surface with radiation. Complex molecules could be broken apart, and life, if it existed, could be extinguished in an instant. Scientists studying the history of Earth have even considered whether gamma ray bursts may have played a role in past extinction. One hypothesis suggests that a burst about 450 million years ago might have triggered a dramatic cooling of the planet, setting the stage for one of the great die-offs of marine life. The evidence is indirect, but the possibility lingers like a shadow in Earth's deep history. What makes gamma ray bursts both haunting and fascinating is their unpredictability. They flare without warning, and because their light is often obscured by dust or distance, many pass unseen. Astronomers have built satellites dedicated to catching them, scanning the sky for sudden flashes of high-energy radiation. When a burst is detected, telescopes around the world swing into action, racing to capture the fading afterglow. These afterglows, glowing in X-rays, visible light, and radio waves, help scientists trace the burst to their host galaxies and uncover the violent events that birthed them. In the cosmic balance, gamma-ray bursts are both destructive and creative. The same explosions that unleash so much energy also scatter heavy elements into space, seeding galaxies with the ingredients needed for planets and life. Gold, platinum, and other precious elements may owe their existence to the very collisions that produce short gamma-ray bursts. Out of destruction, new worlds are born. Gamma-ray bursts remain one of the universe's most breathtaking mysteries. In a matter of seconds, they can outshine billions of stars, sterilize planets, and alter the course of life. They are the ultimate cosmic lighthouses, flashing across unimaginable distances, reminding us of the raw power that still stirs in the hearts of dying stars and colliding remnants. From the quiet darkness of space, particles race toward Earth at unimaginable speeds. Most of them are ordinary cosmic rays, the high-energy fragments of atoms hurled outward by exploding stars. They stream through our atmosphere constantly, a gentle rain of subatomic travelers. But among this rain are rare intruders so powerful that they defy explanation. These are the ultra-high energy cosmic rays, particles carrying energies so extreme that they seem impossible according to the laws of physics we know. The story of these strange visitors begins in the late 20th century. In 1962, a detector in New Mexico recorded a single cosmic ray with energy unlike anything measured before. The particle struck the atmosphere with such force that it released a shower of secondary particles across the detectors on the ground. Its energy was equivalent to a baseball traveling at highway speed, yet all of it was packed into a single subatomic particle. For comparison, particle accelerators like the Large Hadron Collider, the most powerful machines humans have ever built, cannot come close to reaching that level. The numbers stunned physicists. Over the years, other detections followed, confirming that these were not accidents or glitches. Ultra-high energy cosmic rays really do exist, arriving unpredictably from the depths of space. Their energies exceed 10 to the 20th electron volts, a scale so vast it is difficult to picture. Scientists sometimes explain it by saying that one of these particles carries more energy than a well-struck tennis ball, yet it is smaller than an atom. Because of their sheer improbability, one of these particles was famously nicknamed the "Oh my God" particle when it was detected in 1991. It arrived with such staggering energy that researchers could scarcely believe the reading. Yet the event was real, and it forced physics to confront a new mystery. Where could such a particle come from? The problem is that our current models suggest that particles should not be able to reach such energies. The universe places limits because as particles travel through the cosmic microwave background, the faint afterglow of the Big Bang, they should lose energy in collisions with those low-energy photons. This limit is called the Greisen-Satze pin, Kuzmin, or GZK cutoff. According to theory, no particle should arrive at Earth with energies above this barrier. And yet, the Oh my God particle and others like it cross that threshold with ease. Astronomers have searched for the sources of these particles, pointing telescopes toward the regions of sky from which they seem to arrive. Some theories suggest that they may be born near the most extreme environments in the universe, such as supermassive black holes with powerful jets, or the shock waves of exploding stars, much larger than our Sun. Others propose even stranger origins, perhaps linked to exotic physics beyond what we know decays of hypothetical particles from the earliest moments of the universe or processes tied to dark matter. Despite decades of study, no definitive source has been identified. The paths of these particles are bent by magnetic fields as they travel across space, making it nearly impossible to trace them directly back to where they began. By the time they reach Earth, their directions are blurred, like arrows twisted in flight. All we know for certain is that they come from outside our galaxy, crossing immense distances to strike our atmosphere with the energy of a small stone hurled at speed. To catch these rare arrivals, scientists have built enormous detectors, some spread across wide fields of land. The Pierre Auger Observatory in Argentina, for example, covers an area larger than some countries, using tanks of water and arrays of sensors to detect the particle showers produced when cosmic rays hit the atmosphere. Even with such vast instruments, ultra-high energy cosmic rays are few and far between. On average, only one may strike a square kilometer of Earth in a century. Yet each one carries a riddle written in energy. The existence of these particles challenges our understanding of physics itself. They should not exist, at least not in the form we observe. Yet they do, arriving silently from the dark, each one a messenger from realms of energy far beyond what our laboratories can reach. To detect one is to glimpse a force of nature at its most raw, and to be reminded that the universe still holds mysteries powerful enough to bend the very rules we thought unbreakable. When we look at the night sky, the stars seem scattered, as if they were placed randomly across the dark. Yet, when astronomers zoom out far enough, far beyond any single galaxy, they begin to see a hidden order. The universe, when viewed on the largest scales, is not chaotic, but woven together in a delicate pattern known as the cosmic web. It is a vast network of filaments, threads of dark matter and galaxies stretched across unimaginable distances with enormous empty spaces between them. The idea of this hidden web emerged slowly as astronomers began mapping galaxies in 3 dimensions. Early surveys revealed clusters of galaxies clumping together, but it was only when large-scale surveys were conducted in the late 20th century that the true structure was revealed. Galaxies were not spread evenly like dust in the air. Instead, they formed along filaments, strung together like beads on invisible threads. Between these threads were enormous voids, expanses so empty that entire clusters of galaxies seemed to be missing. The scale of the cosmic web is almost beyond comprehension. Filaments stretch for hundreds of millions of light years, crossing one another at dense intersections called nodes, where clusters of galaxies form. The voids in between can span distances equally vast, silent bubbles where almost nothing exists. To map this structure is like looking at the skeleton of the universe, the underlying framework that holds everything together. The web is woven primarily from dark matter, the unseen substance that outweighs visible matter by more than 5 to 1. Although dark matter cannot be seen directly, its gravity shapes the cosmos. It gathers into filaments, pulling ordinary matter along with it. Over time, gas flows into these invisible threads, condenses, and forms stars and galaxies. In this way, the cosmic web is not only the scaffolding of the universe, but also the nursery where galaxies are born and guided into their places. Astronomers study the cosmic web by observing how light from distant galaxies bends as it passes through regions filled with dark matter. This bending, known as weak gravitational lensing, allows scientists to sketch the outlines of the invisible filaments. In recent years, computer simulations have also helped bring the web to life, showing how the universe grew from the nearly uniform sea of particles after the Big Bang into the intricate structure we see today. The filaments act like rivers, guiding matter into dense junctions where galaxies ignite and cluster together. The vast empty voids between the filaments are as important as the filaments themselves. These cosmic deserts may appear empty, but they shape how matter flows, channeling it toward the denser regions. The contrast between abundance and absence gives the universe its texture, a balance of crowded highways, of galaxies, and quiet expanses of nearly nothing. Without the voids, the filaments would not stand out, and without the filaments, the voids would lose their meaning. Together they form a pattern both haunting and beautiful. In some ways, the cosmic web resembles a living system. Matter flows along its strands like nutrients through veins, clustering at nodes the way cells gather in a body. Energy travels across it, carried by light and particles. The universe is not static but dynamic, with the web acting as the great structure that directs growth and movement on scales too vast for human imagination. When astronomers look at the cosmic web, they are not only seeing the present but also glimpsing the past. The filaments grew out of tiny fluctuations in the early universe, ripples in density that slowly expanded over billions of years. Those ancient ripples became the highways of matter we see today, frozen traces of the universe's earliest moments written across the cosmos. To picture the cosmic web is to imagine a net of nearly infinite scale, glowing threads spanning the darkness, each intersection alive with galaxies. It is the hidden architecture of the universe, guiding the dance of stars, shaping the flow of matter, and reminding us that even the emptiest spaces are part of a grand design. Spaceflight is often described as the most precise of human endeavors. A spacecraft leaving Earth must travel at extraordinary speed, follow carefully calculated arcs, and obey the relentless pull of gravity. Every maneuver is planned down to fractions of a second, and every trajectory is tested by computer models before it ever unfolds in the silent dark. Yet, despite this precision, there have been moments when spacecraft did not behave as expected. Subtle shifts in speed, puzzling deviations in trajectory, and unexplained drifts have left scientists with questions that still linger. These are the orbital mysteries, the small but persistent clues that space does not always play by the rules we think we know. One of the strangest puzzles appears during planetary flybys. Spacecraft often use the gravity of planets like Earth, Venus, or Jupiter to gain speed without burning extra fuel. The technique, called a gravity assist, is one of the most efficient tools for deep space exploration. But on several occasions, when spacecraft swung past Earth, they left with a velocity that did not quite match predictions. The difference was small, sometimes just a few millimeters per second, yet in the realm of orbital mechanics, even the tiniest shift matters. These unexplained boosts or slowdowns became known as flyby anomalies. The most famous case came in the late 1990s, when the Galileo spacecraft, en route to Jupiter, performed an Earth flyby. After the maneuver, scientists noticed it was moving slightly faster than models allowed. Years later, the Near-Shoemaker probe, bound for the asteroid Eros, showed a similar quirk. Rosetta, the European comet chaser, also left Earth with an unexpected change in speed. Engineers checked for mistakes in programming, uncertainties in Earth's rotation, even air resistance from the faint upper atmosphere. None of these explanations fit. The anomalies remained, like whispers of hidden forces nudging the spacecraft as they passed. Even more enduring was the Pioneer Anomaly. The twin Pioneer probes, launched in the early 1970s, were among the first spacecraft to leave the inner solar system. For decades, they faithfully transmitted data back to Earth as they drifted toward the outer reaches, far beyond the orbit of Pluto. But as scientists tracked their trajectories with increasing precision, they noticed something odd. Both Pioneer 10 and Pioneer 11 were slowing down ever so slightly, as if a faint hand were tugging them back toward the sunlight. The effect was tiny, a deceleration measured at less than 1 nanometer per second squared, but it persisted for years and defied easy explanation. The mystery of the Pioneer Anomaly became a kind of scientific legend. Some speculated that it hinted at new physics, perhaps a flaw in our understanding of gravity itself. Others wondered if the spacecraft were feeling a drag from interplanetary dust, or if dark matter might be at play. Teams of physicists and engineers pored over decades of telemetry, looking for patterns. The anomaly became a reminder that even in the precise world of spacecraft navigation, something as small as an unaccounted for force could grow into a profound puzzle. Eventually, after years of careful work, many scientists came to believe the answer lay not in exotic new physics, but in the spacecraft themselves. The Pioneers were powered by radioisotope generators, which gave off heat unevenly. This radiation, when emitted in one direction more than another, acted like a tiny thrust, slowing the probes in a way that mimicked a gravitational pull. The explanation was elegant, but it did not erase the fascination. For decades, the anomaly had stood as a window into the unknown, sparking imagination and keeping open the possibility that the universe still held surprises in its most familiar forces. Precision measurements have revealed other subtle mysteries as well. When spacecraft orbit the Moon or Mars, tiny wobbles in their paths sometimes betray hidden masses beneath the surface, concentrations of dense rock or metal buried deep underground. Around Earth, satellites occasionally detect unanticipated drifts, which turn out to be linked to fluctuations in the planet's gravity field as oceans rise and fall, or as ice sheets melt and redistribute weight across the globe. These mysteries, though often explained in time, remind us how delicately spacecraft respond to every tug and pull in their environment. Orbital anomalies capture attention because they blur the line between engineering error and natural mystery. They are found in the faint residue of numbers, in the decimal places of velocity and distance. Yet behind those decimals may lie entire chapters of physics waiting to be understood. Sometimes the solution is mundane, like heat radiating from a spacecraft's engine. Sometimes it is profound, revealing unseen features of a planet or even shaping our theories of gravity. And sometimes the questions linger, unanswered, keeping alive the sense that even the closest orbits around Earth hold secrets that science has not fully grasped. On the far side of the Moon, hidden from Earth's direct gaze, lies a scar unlike any other in the solar system. It is called the South Pole Aitken Basin, and it is the deepest and one of the oldest known impact sites in our cosmic neighborhood. Spanning roughly 1/4 of the Moon's entire surface, it stretches across more than 2,000 kilometers, with a depth of over 12 kilometers at its deepest points. Imagine an impact so powerful that it reshaped nearly an entire hemisphere. This was no ordinary crater, but an ancient wound carved into the lunar crust, leaving behind a basin that has fascinated scientists for decades. For a long time, the South Pole Aitken Basin was simply a feature on lunar maps, a colossal depression visible in orbiting imagery. But as spacecraft began to measure the Moon's gravity more precisely, something strange emerged from the data. Within this vast basin were regions where gravity was unexpectedly stronger, places where spacecraft felt a subtle, invisible tug. These anomalies, called mass concentrations or mascons, puzzled researchers. The moon should have been a relatively predictable body, yet these hidden weights pulled spacecraft off their intended paths, forcing engineers to make careful corrections during missions. The discovery of mascons goes back to the 1960s during the era of the Lunar Orbiter missions. As these probes circled the moon, their orbits began to drift in odd ways. Scientists realized that the changes could only be explained if certain regions of the lunar crust contained dense material buried beneath the surface. The South Pole Aitken Basin, with its immense scale, contained some of the most striking of these anomalies. What caused them has been the subject of debate. One possibility is that when the colossal asteroid or comet slammed into the moon billions of years ago, it left behind dense rock pushed up from the mantle, trapped beneath the basin's floor. Another theory suggests that metal-rich material, possibly fragments of the impacting body itself, became buried there. Some even imagine that the moon's crust thinned during the collision, allowing heavier mantle rock to rise closer to the surface, where it now lurks as a hidden weight. Whatever the source, these mascons have real effects. Spacecraft flying low over the basin feel their pull, their orbits subtly bending, like a leaf caught in a faint current. In recent years, missions such as NASA's GRAIL twin spacecraft have mapped the moon's gravity field in extraordinary detail. They confirmed that the South Pole Aitken Basin is not just large and deep, but also riddled with these strange concentrations. GRAIL's data revealed that beneath the basin lies a buried mass so immense it could weigh as much as several times that of Mount Everest. This hidden presence adds to the mystery of how the basin formed and what it tells us about the moon's violent history. The implications reach far beyond curiosity. Any future missions that aim to land or orbit near the basin must account for the gravitational quirks. A spacecraft entering its field without preparation could find itself pulled into unexpected paths, wasting fuel or risking navigational errors. Engineers designing lunar orbits must carefully weave their trajectories to avoid these subtle but significant distortions. In this way, the South Pole Aitken Basin serves as both a scientific enigma and a practical challenge for exploration. The basin is also a window into the deep past of the solar system. Its size suggests an impact that occurred during the early days of planetary formation when colossal collisions were common. Studying it could reveal the composition of the moon's mantle and even offer clues about Earth's own early history, since the two worlds have shared much of their cosmic journey. Yet, despite all we have learned, the buried mass beneath the basin remains unexplained in detail. It is a hidden weight pressing from below, silent but undeniable. The far side of the moon, where the basin rests, has long been a place of mystery. Shielded from Earth's radio signals and human eyes, it remains the quietest place in near space. To place such a vast and puzzling structure there only deepens the sense of wonder. The South Pole Aitken Basin is not just a hole in the lunar surface. It is a story written in gravity, a silent reminder of the forces that shaped the worlds we see today. When explorers first dreamed of sending probes to Mars, they imagined a world whose mysteries would be painted in dust, storms and canyons, mountains and valleys. Few expected that one of its strangest puzzles would be invisible, written not on the planet's surface, but within its very crust. Unlike Earth, Mars has no global magnetic shield. Billions of years ago, its dynamo shut down, leaving the planet exposed to the solar wind. Yet, Scattered across its surface are faint echoes of that ancient protection, preserved in the rocks as magnetic patches. These magnetic fragments are not evenly spread, nor are they gentle whispers. They are abrupt and local, twisting and curling in strange ways that make the Martian crust resemble a patchwork quilt stitched together from fragments of its magnetic past. When orbiters began to sweep low over these regions, their instruments caught the signatures of fields that rose and fell sharply. Sometimes the direction of magnetism even reversed within just a few kilometers. It was as if the planet itself were scarred with invisible fingerprints of its early history. The story began to unfold with NASA's Mars Global Surveyor in the late 1990s. As the spacecraft mapped the magnetic environment, scientists were astonished to find fields stronger than expected, locked into the planet's crust. These were not subtle variations. In some regions, the strength of the magnetic field rivaled or even exceeded what might be measured on Earth's surface. Yet, only a few kilometers away, the signal could drop close to zero. Such abrupt changes made Mars feel unpredictable, a world whose invisible forces shifted as erratically as its dust storms. These magnetic patches can be disruptive. Instruments designed to measure the surface or atmosphere sometimes struggle to filter out the interference. Orbiters that attempt to map the terrain or trace mineral deposits must compensate for the invisible tug of these fields. Even navigation can become more complex, as a spacecraft flying across Mars might suddenly detect an unexpected twist in the data. On Earth, magnetic anomalies are often tied to mineral deposits or ancient lava flows. On Mars, they tell of a once living dynamo deep in the core, a system that churned for billions of years before finally fading away. Scientists believe that when Mars still had its magnetic dynamo, volcanic activity spread vast sheets of lava across the crust. As these layers cooled, they locked in the direction of the magnetic field, preserving it like a fossil. Over time, as eruptions piled one flow on top of another, the magnetic directions layered too, sometimes pointing north, sometimes south. When the dynamo shut down, the field disappeared, but the crust kept its memory. Today, orbiters detect these ghostly fragments, like embers from a long-dead fire, still glowing faintly beneath the surface. The uneven nature of these patches has created a planetary map unlike any other. In the southern hemisphere, the crust is older and thicker, and here the magnetism is especially strong. In the northern plains, where the surface is younger and shaped by more recent impacts and flows, the magnetic memory is weaker or absent. This contrast has led scientists to suspect that the history of Mars may have been more violent and complex than once imagined. Massive collisions could have shattered parts of its crust, erasing their magnetic record. Elsewhere, long-lived volcanic activity may have preserved stronger signatures. The beauty of these hidden fields is that they do more than disrupt spacecraft. They offer clues to the deep past. By studying them, scientists can piece together when Mars lost its dynamo, how its interior cooled, and what role catastrophic impacts may have played. They may even help explain why Mars, once warm and wet, became the cold desert we see today. Without a global magnetic shield, its atmosphere was slowly stripped away by the relentless solar wind, leaving behind a world marked by scars, both visible and invisible. Orbiters continue to chart these magnetic puzzles with greater precision. Their data reveal patterns that resemble stripes across the crust, much like those on the floor of Earth's oceans, where tectonic plates spread apart. On Earth, these stripes record the history of magnetic pole reversals. On Mars, they may represent a similar process, frozen in time, an echo of a magnetic past that no longer shifts or flows. The planet has become a fossil, not only in its rocks and valleys, but in the magnetism buried beneath its surface. The invisible quilt of fields across Mars is more than a scientific curiosity. For future explorers, it will be a landscape of unseen hazards and subtle surprises. A rover on the ground may never notice them, but orbiters circling above will continue to feel their pull, their sensors bending to the whispers of a shield that once guarded a living planet. Among the planets of our solar system, none commands a magnetic presence like Jupiter. Earth's magnetic field feels mighty to us, large enough to wrap the planet in a protective cocoon, but Jupiter's field exists on a scale that almost defies imagination. If it were visible to the eye, its outline would stretch millions of kilometers into space, so wide that it would encompass dozens of moons and brush against the orbit of Saturn itself. It is the largest single planetary structure in the solar system, created not from stone or atmosphere, but from invisible lines of force. The source of this staggering magnetosphere lies in Jupiter's interior, deep within, under crushing pressures that turn hydrogen into something strange and metallic, lies a restless ocean of liquid metal. Unlike Earth, where liquid iron in the core stirs the field into being, Jupiter's metallic hydrogen churns and flows with incredible speed. The planet spins once every 10 hours, dragging this conducting fluid into motion, generating currents vast enough to forge a magnetic field 20,000 times stronger than Earth's. From that hidden heart, the field blossoms outward, carving space itself into zones of immense power. Yet this shield is not gentle. Where Earth's field deflects and shelters, Jupiter's field captures and amplifies. It sweeps up charged particles from the solar wind and from Io, Jupiter's volcanic moon, which spits sulfur and gas into space in great plumes. Once caught, these particles are whipped around the planet in violent spirals. They are accelerated to near the speed of light, trapped in belts of radiation so intense that they make Earth's Van Allen belts look faint by comparison. In this storm, every orbiting object is under constant assault. For spacecraft, entering Jupiter's magnetosphere is like sailing into a hurricane made of radiation. Circuits fail, sensors are blinded, memory can be erased in an instant as invisible particles penetrate electronics and flip the very bits that store information. A spacecraft unprepared for this environment would be reduced to silence long before completing its mission. That is why every probe sent to Jupiter must be designed with extraordinary care. NASA's Juno spacecraft, launched in 2011, is the boldest example. To survive in this radiation ocean, Juno carries a special titanium vault weighing nearly 400 kilograms that houses its most sensitive electronics. The metal walls are nearly a centimeter thick, a shield against the barrage of charged particles. But even this protection is not enough by itself. Juno's path around Jupiter was chosen with surgical precision. Instead of circling close like a steady satellite, it follows a long, looping orbit that dives in close for just a few hours of observation, then swings far back out again. These fleeting encounters allow it to gather data without lingering too long in the most dangerous zones. Each flyby is a careful dance, like a ship weaving between reefs, knowing that one wrong move could spell disaster. Radiation levels near Jupiter are measured in doses that would disable ordinary satellites within weeks. Even Juno, with its vault and evasive maneuvers, is not immune. The cumulative toll of each orbit gradually wears on its systems, eating away at its lifespan. The mission was designed knowing this. Juno would survive long enough to make a series of daring passes, but eventually, the invisible storm would claim its strength. The scale of the magnetosphere reaches beyond spacecraft to shape the very moons of Jupiter. Io's volcanoes feed a ring of plasma that circles the planet, glowing in radio waves detectable from Earth. Europa, with its hidden ocean, is constantly bombarded, its icy crust scarred by radiation chemistry that stains it in colors we can see through telescopes. Even Ganymede, the largest moon in the solar system, carries its own magnetic field, born in part as a defense against Jupiter's relentless assault. This vast machinery of magnetism produces its own light show as well. At Jupiter's poles, the auroras shine not in brief flashes as they do on Earth, but in permanent ovals of blue and ultraviolet flame. They are powered not by the occasional gust of solar wind, but by the endless churn of particles trapped in Jupiter's field. From space, these auroras appear as glowing halos encircling the planet's poles, bright enough to outshine the northern lights of our world many times over. Exploring Jupiter and its moons means confronting this colossal force directly. Any lander sent to Europa, for example, would need to be heavily shielded just to survive for days on the surface. Orbiters designed to linger must either fly in and out of the field or accept short lifetimes before the radiation eats away at their electronics. Human exploration here is not yet practical. The sheer intensity of the environment demands technology we do not yet possess. Jupiter's magnetosphere is both wonder and warning. It shows us how nature can build structures larger than planets themselves, sculpted by physics on an unimaginable scale. But it also reminds us that not all beauty in space is welcoming. Sometimes the brightest auroras and the grandest shields conceal an ocean of danger, a realm where machines tremble and only careful choreography allows survival. Among the giant planets, Saturn holds a special place in human imagination. Its shimmering rings, delicate and bright, have made it a symbol of cosmic beauty for centuries. But beyond their visual splendor, Saturn conceals mysteries that continue to puzzle even the most advanced spacecraft. Beneath the rings lies a magnetic world that defies expectations, as though the planet has chosen to keep some of its secrets carefully hidden. Every planet with a magnetic field tends to tilt that field slightly from the axis of rotation. Earth, for example, spins around its axis, but its magnetic poles are offset, leading to the drifting of compass needles and the slow migration of magnetic north. Jupiter's field is tilted as well, as are those of Uranus and Neptune, yet Saturn is different. Its magnetic field is aligned almost perfectly with its spin axis, so much so that instruments searching for the tilt could not find one. This alignment creates a puzzle. According to the laws of planetary physics, a magnetic field cannot remain stable without some degree of tilt. A slight wobble is necessary to sustain the dynamo action deep within the planet that generates the field. Without it, theory suggests that the field should fade away. Yet Saturn's magnetic field remains strong, symmetric, and steady. For scientists, it is like listening for an echo in a canyon and hearing silence where there should be sound. The dynamo is clearly working, but the rules by which it operates may not be the ones we expect. The Cassini spacecraft, which orbited Saturn for more than 13 years, carried some of the most sensitive instruments ever flown. Cassini was designed to probe Saturn's rings, moons, and magnetic environment in detail. Over the course of its long mission, it gathered streams of data, some of which clarified old mysteries, while others opened entirely new ones. One of Cassini's most perplexing findings was that Saturn's magnetic field showed no detectable tilt at all, not even a fraction of a degree. It was as if the planet's deep interior had found a way to bend the rules of physics, creating a magnetic cloak that was both elegant and baffling. The magnetosphere around Saturn, shaped by this unusual field, also held surprises. Within it, radiation belts swirled in ways that did not match predictions. Saturn's rings, composed mostly of ice, act as barriers that absorb particles, altering the shape of the belts. Yet Cassini found fluctuations that could not be explained solely by the rings. Sometimes the belts seemed to swell unexpectedly, filled with particles of unexplained origin. At other times, radiation levels dropped without clear cause. The behavior suggested that unseen processes were feeding or draining the belts, processes that scientists are still working to understand. The rings themselves added another layer of intrigue. Cassini's instruments discovered that the rings are not passive, silent bands of ice, but active participants in Saturn's magnetic story. Streams of water vapor and dust particles trickle down from the rings into the planet's upper atmosphere, altering its chemistry. These ring rains, as they are sometimes called, also influence the magnetic environment, injecting new material into regions once thought to be stable. It was as though the rings were not just ornaments, but dynamic actors, constantly reshaping Saturn's surroundings. Even the timing of Saturn's rotation, something that should be straightforward, became a puzzle. Cassini measured tiny variations in the planet's radio emissions, the signals produced by its magnetic field. These emissions shifted over time, making it difficult to pin down Saturn's true day length. The variations seemed tied to the interactions between the magnetic field, the rings, and even the icy moon Enceladus, whose geysers of water feed Saturn's magnetosphere. In effect, the planet's heartbeat was masked by the rhythms of its companions. By the end of its mission, Cassini had rewritten much of what we thought we knew about Saturn, yet some of its most important questions remained unanswered. Why is the magnetic field so perfectly aligned? What invisible forces shape the radiation belts? How do the rings and moons weave themselves into the planet's magnetic fabric? The spacecraft's final plunge into Saturn's atmosphere in 2017 was a deliberate act designed to prevent contamination of moons that might host life. In those final moments, as Cassini transmitted its last signals, it carried with it puzzles that scientists may not solve for decades. Saturn, with its golden rings and hidden complexities, remains a world of contrasts. Outwardly serene, inwardly enigmatic, it reminds us that even beauty can conceal layers of mystery. Across the vastness of the universe, we listen. Giant radio dishes stand like metal flowers, their open mouths tilted toward the heavens, collecting whispers from the stars. With them, astronomers hear the hiss of cosmic background radiation, the rhythmic pulses of distant pulsars, and the faint signals of galaxies stretched thin by the universe's expansion. Yet sometimes, when the listening is at its most careful, the universe falls strangely quiet. There are regions where the signals vanish, where the steady hum of the cosmos is replaced by silence, as though someone has placed a veil between us and the stars. These radio silence zones do not always appear in the same way. Sometimes they are broad swaths of sky, where signals are unusually faint, as if something between Earth and the source is scattering or absorbing them. At other times, they are localized pockets, moments when a spacecraft, drifting through space, passes into a region where its transmissions flicker or its instruments pick up nothing at all. For astronomers, these silences are not peaceful but puzzling, a reminder that space itself is not a perfect void but an active, restless medium. One of the main culprits is plasma, the fourth state of matter. Plasma is made of charged particles, free electrons, and ions that move and respond to magnetic fields. It fills the space between planets and stars, carried outward from suns in streams called stellar winds. On Earth, plasma makes up the auroras that shimmer near the poles. In space, it creates invisible seas through which light and radio waves must travel. When radio waves encounter plasma, they can bend, scatter, or even be absorbed. Sometimes the effect is mild, no more than a gentle distortion. But in certain regions where plasma density is high, signals vanish entirely. A pulsar's once reliable heartbeat might seem to skip, or a spacecraft's message back to Earth might arrive garbled or not at all. To those who study the sky, these silences are like gaps in a conversation, places where the voice of the universe is muffled. Magnetic fields play their part as well. The universe is threaded with invisible lines of force, stretching between stars, draped around planets, and woven through entire galaxies. When radio signals cross these fields, they twist in subtle ways, a phenomenon known as Faraday rotation. In extreme cases, the twisting grows so strong that the original signal is lost, buried in noise. For astronomers, this can make regions of space appear strangely quiet, even when energetic processes are unfolding within them. Some of the most baffling silences come from beyond our galaxy. When astronomers survey the radio sky, they sometimes encounter vast voids, areas that seem drained of signal. These may be the same cosmic voids revealed by galaxy maps, places where matter itself is sparse. Yet the silence is not simply absence, because even empty space should echo faintly with background radiation. Something else may be shaping the way signals pass through these expanses, bending and filtering them until little remains. Closer to home, spacecraft have also encountered their own zones of silence. Probes orbiting planets or traveling through regions dense with plasma have experienced communication blackouts. During some Mars missions, for instance, spacecraft passing behind the planet enter minutes of radio silence, cut off by distance and interference. Solar storms create similar effects around Earth, briefly overwhelming communication satellites with a flood of charged particles. To those on the ground, the silence feels like an interruption. To scientists, it is another reminder of how alive space really is. For astronomers, these quiet zones can be both frustrating and tantalizing. A sudden loss of signal may hide important data, yet it also hints at hidden structures in space. Each silence carries information, coded in the way signals bend, fade, or vanish. By studying these absences, scientists learn about the plasma seas that flow between stars, the magnetic scaffolding of galaxies, and even the properties of dark matter and energy. The silence itself becomes a teacher, whispering through what it withholds. The universe is often thought of as empty, but in truth, it is a landscape filled with invisible fields and restless seas of particles. Radio silence zones remind us of this. They are not voids without meaning, but regions where the universe's deeper layers reveal themselves in unexpected ways. To listen to the cosmos is not always to hear, but sometimes to notice what cannot be heard. In the evening sky, Venus shines with a brilliance unmatched by any planet. It glows as the evening star, often the first light to appear after sunset and the last to fade before dawn. From Earth, it looks serene, almost gentle, a twin of our world in size and mass. Yet this dazzling world hides a story of loss. Beneath the glow of its clouds lies a furnace, a planet transformed by the absence of a shield that its sister Earth has always carried. For all their similarities, Venus and Earth diverged along very different paths. Earth has oceans that cradle life, a climate that allows forests and deserts, and ice, and an atmosphere gentle enough to breathe. Venus has none of this. Its surface is scorched by heat so intense it could melt lead. Its air is thick with carbon dioxide, pressing down with a weight more than 90 times the pressure at sea level on Earth. Above, Clouds of sulfuric acid swirl in layers that blot out the sun entirely. One of the deepest reasons for this difference lies in what Venus lacks. Unlike Earth, it does not have a global magnetic field to guard its atmosphere. Instead of being wrapped in an invisible cocoon, Venus is left almost bare to the solar wind, a stream of particles that flows outward from the sun. Over billions of years, this unrelenting exposure has stripped away much of what may once have made Venus habitable. Evidence suggests that Venus was not always so inhospitable. In its early history, scientists believe it may have had shallow oceans. For a time, it might have looked not so different from Earth, with liquid water pooled on its surface and clouds carrying rains that fed those seas. But the sun's light broke apart water molecules in the upper atmosphere. Hydrogen, the lightest of elements, drifted away into space, lost forever. Without hydrogen, water could not reform. The seas evaporated, the air grew heavy with carbon dioxide, and a runaway greenhouse effect took hold. Spacecraft that have visited Venus have confirmed the traces of this atmospheric escape. Instruments aboard orbiters detected particles streaming away into space, a slow bleed of what little remains of Venus's lighter gases. What Earth's shield deflects, Venus has endured directly. The result is a planet locked in an irreversible transformation, one that turned a possible cradle of life into a furnace. The contrast between Earth and Venus is stark. On Earth, the oceans remain, held in place by a protective balance. Our magnetic field and atmosphere together form a double barrier that keeps the solar wind at bay and allows liquid water to persist. Venus shows us what happens when that balance is broken. It is a world where oceans boiled away, where the air grew heavy and toxic, and where the surface became a desert of fire and rock. The story of Venus is not only about its past, but also about its warning for the future. Its thick atmosphere traps heat with such efficiency that the planet became the hottest in the solar system, even hotter than Mercury, which lies closer to the Sun. The lesson is clear: a planet's climate can be tipped into extremes by the smallest of shifts, and once the balance is lost, recovery is nearly impossible. This ruined twin also informs the search for life beyond our solar system. Astronomers have found countless exoplanets that resemble Earth in size and distance from their stars, but resemblance is not enough. Without protection, even a promising world Denon can become uninhabitable. Venus reminds us that habitability is shaped not only by where a planet sits in its system, but by how well it holds on to its air and water. What we see in the night sky as a steady, guiding light is in truth a cautionary tale. Venus is the story of a world that might have been a sister to Earth, but became something entirely different. Its beauty hides a furnace, its glow conceals a warning, and its silence tells us that survival depends on more than just distance from the sun. It depends on the invisible defenses that keep a planet's heart alive. When astronomers first began to search for planets beyond our solar system, many expected to find familiar worlds. They imagined cousins of Earth circling suns like our own, or perhaps gas giants resembling Jupiter drifting at comfortable distances. What they discovered instead was stranger and far more varied than anyone predicted. Exoplanets, as they are called, have revealed themselves to be wanderers of unusual orbits, tilted in unexpected ways, and wrapped in atmospheres that defy the imagination. Some of the earliest surprises came from planets known as hot Jupiters. These are massive gas giants, similar in size to Jupiter, yet orbiting so close to their stars that a single year lasts only a few days. Their skies blaze with temperatures hot enough to melt metal, and their swollen atmospheres are constantly being blasted by stellar winds. In some cases, these atmospheres are stripped away, streaming into space like long glowing tails. To astronomers, it was as if they had found Jupiter in the impossible position of Mercury, a reminder that the universe does not always follow the patterns seen at home. Other exoplanets revealed orbits so elongated that they sweep far from their stars before plunging back in again, like cosmic comets on grand scales. Some move in paths tilted steeply compared to their star's equator, suggesting that violent encounters or gravitational tugs from unseen companions once altered their courses. A few even orbit backwards, moving against the spin of the stars they circle. These strange geometries show that planetary systems can be chaotic, shaped by collisions, migrations, and forces that disrupt any sense of order. Even the way some of these worlds spin is unusual. While Earth's axis tilts gently, giving rise to our seasons, other planets are tipped at wild angles. Uranus in our own solar system lies almost on its side, but exoplanet surveys suggest such extreme tilts may be common elsewhere as well. A tilted axis can mean climates of dramatic swings or strange patterns of day and night where the sun never rises or sets in familiar ways. For any potential life clinging to such a world, existence would unfold under skies unlike any we have known. Radiation storms add another layer of challenge. Many stars flare more violently than our Sun, releasing bursts of energy strong enough to strip atmospheres and bathe their planets in deadly radiation. Red dwarf stars, the most common stars in our galaxy, often unleash storms that can sterilize their inner planets again and again. Worlds orbiting these stars may lie within the so-called habitable zone, where temperatures should allow liquid water, yet their surfaces may be scorched too often to sustain life. For scientists, this paradox is a sobering reminder that habitability is not simply a question of distance from a star, but of protection from its tempests. Amid these findings, a haunting thought arises. If Earth itself harbors the South Atlantic Anomaly, a place where magnetic defenses falter and radiation surges inward, could exoplanets carry their own versions of such traps? Invisible zones where spacecraft might one day falter, or where local conditions create magnetic dead spots. The cosmic ocean may be littered not only with planets, but with hidden reefs of radiation and magnetism, dangers we cannot yet see, but which shape the futures of those worlds. The more astronomers look, the more they find anomalies that stretch the imagination. Planets made mostly of water, with no land at all, drifting beneath endless global oceans. Others are thought to rain glass, the sharp fragments driven sideways by supersonic winds. There are carbon-rich planets where diamond could form deep within the mantle, and scorched lava worlds where entire surfaces glow red with molten rock. Each discovery pushes the boundaries of what a planet can be, and reminds us that Earth's balance of conditions is rare and delicate. As our instruments grow sharper, the catalog of exoplanets expands by thousands, each with its own story written in orbit and atmosphere. Among them are worlds that may one day host telescopes or even explorers, and others that remain as unreachable warnings of how nature can twist the familiar into the strange. The search is young and the mysteries are deep, but already it is clear that the universe is not filled with replicas of Earth. It is filled with wonders and anomalies, planets that reveal the wild creativity of cosmic evolution. The dream of leaving Earth has always carried with it both wonder and risk. From the first rockets that pierced the sky to the vast plans for settlements on Mars or missions to the icy moons of the outer solar system, human imagination has always reached for the stars. Yet as we learn more about the cosmos, one truth grows clearer. Space is not empty. It is filled with unseen currents, hidden reefs, and anomalies that will shape the future of every journey. The mysteries we have uncovered so far are only the beginning, and they remind us that exploration is never simple. When spacecraft cross the South Atlantic Anomaly, instruments flicker and sometimes fail. When probes drift near Jupiter or Saturn, radiation belts surge with deadly energy. Even within the relative safety of Earth's orbit, astronauts encounter strange flashes of light in their vision, caused by cosmic rays passing directly through their eyes. These experiences reveal a sobering reality. To travel deeper into space, humans must carry protection not just against the cold and vacuum, but against the invisible hazards woven into the very fabric of the universe. Shielding spacecraft will be one of the greatest challenges. Ordinary metal walls can block some particles, but high-energy cosmic rays pass through as though they were paper. Engineers have begun to experiment with layered shielding, magnetic fields, and even water or hydrogen-rich materials to slow the radiation's progress. Some designs imagine spacecraft wrapped in fluid-filled walls, turning the ship itself into a moving shield. Others look to the idea of artificial magnetic bubbles, small magnetospheres generated by the spacecraft to mimic Earth's protective field. These ideas are ambitious, but they may be essential if humans are to spend months or years traveling between planets. The risks extend beyond radiation. As spacecraft grow more precise, tiny anomalies become more noticeable. A spacecraft swinging around Earth for a gravity assist sometimes speeds up by fractions of a millimeter per second more than predicted, or slows in ways no equation can fully explain. Over great distances, even such subtle deviations can add up, leading to navigational uncertainty. For crewed missions, such uncertainties are more than math problems. They could mean the difference between reaching a planet and drifting endlessly past it. Preparing for the unexpected, with flexible systems and constant monitoring, will be as important as the rockets themselves. Future missions will also face unknowns we cannot yet describe. The solar system is mapped in broad strokes, but details remain hidden. Mars has crustal magnetic patches that tug unexpectedly on orbiters. The Moon hides mass concentrations beneath its basins that bend trajectories in ways still not fully understood. Beyond our solar system, exoplanets may harbor their own anomalies, traps where radiation or magnetic storms create invisible barriers. Every new step outward carries with it the possibility of encountering forces that challenge both our machines and our imagination. To prepare, science must walk hand in hand with exploration. Telescopes will scan the skies for patterns in radiation, magnetism, and cosmic flows. Simulations will try to predict how anomalies evolve and where new ones might be found. Robots will scout the most dangerous zones first, absorbing risks before humans arrive. Each layer of knowledge will act like another thread in the protective fabric we weave around our species, a fabric that may one day stretch from Earth to Mars and beyond. Yet even as we design shields and map invisible fields, there is an element of humility that must guide our steps. We cannot assume that space will ever be fully predictable. The anomalies we have discovered so far remind us that the cosmos holds surprises too subtle or too vast for our current instruments to capture. Somewhere out there are mysteries waiting to alter our paths, just as the South Atlantic Anomaly does today, just as the silent voids between galaxies shape the flow of stars. The future of human exploration will not be defined only by technology or courage, but by our ability to live with uncertainty. We must learn not only to survive the anomalies we know, but to be ready for the ones we do not. In that sense, every journey outward will be both a voyage of discovery and a negotiation with the unknown. The Bermuda Triangle of space is real, but it is only the beginning. It is not an isolated oddity, nor a quirk of Earth alone, but a reminder that the cosmos is stitched together by forces both visible and unseen. In the skies above South America, satellites flicker, astronauts glimpse phantom sparks, and radiation seeps through a weakness in our planet's shield. This one anomaly alone has challenged decades of spacecraft and left scars on missions worth millions. Yet the more we have looked outward, the more we have found that such anomalies are not rare, but woven into the very structure of the universe. Space is not empty. It is alive with traps, reefs, and mysteries. Invisible belts of radiation wrap planets in dangerous rings. Gravitational voids stretch across millions of light years, swallowing entire regions into silence. Black holes wait as unseen whirlpools, swallowing light and matter without trace. Even the most distant galaxies send strange pulses, brief flickers of energy that arrive without warning and vanish before we can fully grasp them. Everywhere we look, there are signs that the universe is restless, its patterns shifting and twisting in ways that defy our neat equations. For every mystery we have mapped, new ones appear. The South Atlantic Anomaly has grown steadily, shifting its shape like a living shadow. Beyond Earth, Jupiter's magnetosphere crackles with radiation so strong it could erase a human life in an instant. Farther still, we encounter the silent expanse of the Bootes Void, a bubble of almost nothing stretching across hundreds of millions of light years, its emptiness as strange as any abundance. These are not distant curiosities. They are reminders that the universe is as much about absence as it is about presence, about the unseen as much as the seen. The image of the cosmic ocean has never been more fitting. Our planet is like a fragile ship, sheltered within its magnetic harbor, drifting at the edge of vast currents. Around us lie hidden reefs of radiation, whirlpools of gravity, and storms of particles that never sleep. Like the sailors who once feared the Bermuda Triangle on Earth, we are only beginning to chart the hazards of the space that surrounds us. Every journey outward carries us deeper into waters both beautiful and unpredictable. And so we return to the quiet awe that began this story. If anomalies exist so close to us, only a few hundred miles above our heads, what wonders or what dangers will we encounter when we push farther? Will we one day map cosmic triangles beyond our solar system, places where the rules of physics bend in ways we cannot yet imagine? Will future explorers look back at the South Atlantic Anomaly as we now look at ancient maps of oceans, seeing it not as an isolated feature, but as the first hint of a vast pattern waiting to be uncovered? The answers lie ahead, waiting in the deep. For now, all we can do is listen to the whispers of space, measure its silences, and trace the outlines of its invisible structures. Each anomaly, whether a patch of radiation, a gravitational tug, or a flash of light from across the universe, is part of a larger story. A story of a cosmos that is not static but alive, restless and full of secrets. If you have drifted with me this far, through the triangles and voids, through the whispers of radiation and the silence of cosmic reefs, I invite you to keep journeying deeper. If you found wonder in this story, consider giving it a gentle like or tapping subscribe so that more curious minds may stumble upon this little corner of the internet. And if your eyes are still open, I would love to know where you are listening from and what time it is for you. There is something comforting in knowing that, scattered across Earth, people are falling asleep to the same quiet science, at slightly different hours, beneath the same restless sky. Now take one last slow breath and let the mysteries of the universe drift quietly in your thoughts. Our journey will continue through oceans of stars and anomalies yet to be uncovered. But for tonight, let the story rest here, suspended in the silence of space,